Hi, good morning. This is Trina here to discuss about DL configuration, Cis-Trans configuration, racemization. This is the last lecture of stereochemistry. So I hope that you have already gone through the study material. Here the study material, the course page is given, and there you can see not only the study materials, the different problems and the probable questions, and also the solved problems and the semester questions. And also in my personal information, I have given my contact number and email ID. So if you have any doubt, you can communicate with me. So the course name, you know, that is the chemistry, and the subject code CH101 for odd semester, CH201 for even semester. This course is for undergraduate BTech students, and the streams are CSE IT Civil Mechanical for even semester and Electrical EC BME for odd semester. The credits 3, contact hours 35. So weekly I will take 3 lectures. And the prerequisite knowledge required, that is the 12 standard. And the course objective, the students will learn different concepts of chemistry. So here in the course outcome, students will learn the stereochemical representation of different molecules, and they will learn that how stereochemistry, based on the stereochemistry, the physical property, the biological property differs, and also that how the reaction takes place. And this is the lecture plan. So you come to know from this that which topic will be covered in which lecture. And so you can take the prior preparation of this. So here I will cover today, that is the configuration DL, Cis-Trans and racemization. That is the last lecture of stereochemistry. So first lecture already you have learned, that is the module 3 stereochemistry. You have learned the representation of 3-dimensional structure, chirality, optical activity. In the second lecture, you have learned the isomerism, different types of isomerism, structural isomerism and stereoisomerism. In the third lecture, you have learned the enantiomers and the diastereomers. So these are the optical isomers. So you have learned the optical activity and the optical isomers. So in today's lecture, you will learn the configurations, DL configurations, the Cis-Trans configurations, and racemization. So this part is already highlighted. You can see. Okay, now first thing, you have learned different representation, 3-dimensional representation. Okay, so can you remember that what are the representation, 3-dimensional representation you have learned? Different representation you have learned, like say Fisher representation. This is the Fisher representation. You can remember that it is actually the 3-dimensional representation in 2-dimensional way. So here you can see the vertical line and the horizontal line. Next, the Newman representation. Here we get the big circle, that is one carbon, and the back side the small dot carbon. This is the Newman representation. And also you have learned the sawhorse representation. So if it is similar with the Newman representation, if we see from the bottom side, then we get the sawhorse representation and the flying wedge projection. So here the solid line and the dash line, okay, and it is a wedge. So it is the front side, it is towards the viewer, and the dash line, that is the backward side, it is away from the viewer. So this representation already you have learned. Now DL configuration. Okay, so DL configuration, how you can understand. So here in many configuration, here it is the structure of glyceraldehyde is given. So which one is D configuration, which one is L configuration, how you can understand. So here you can observe that OH group at the left side, and in this figure the OH group at the right side. If the OH group at the right side, that is the D-glyceraldehyde. If the OH group is at the left side, that is called L-glyceraldehyde. So in this way, we can understand from the representation that which one is D representation and which one is L representation. So the configuration of D-glyceraldehyde, in which hydroxyl group is attached to the right of the asymmetric carbon center, okay, asymmetric carbon center. So we have to find the asymmetric carbon center, is designated as D, and the configuration of L-glyceraldehyde, in which the hydroxyl group is to the left of the asymmetric carbon, is designated as L. Thus, the complete designation of D-glyceraldehyde is given by DD-glyceraldehyde, D to specify configuration, and D to small d to specify the direction of optical rotation, and L-glyceraldehyde, LL-glyceraldehyde. So here also the capital L shows the configuration and the small l shows the represent the optical rotation. So now I will show one of the video, so you will be more clear about DD and LL configuration. So this is the DL configuration. So take the glyceraldehyde. So glyceraldehyde structure you have seen. This is the glyceraldehyde, and we can represent in different way. So first one, that is the Fisher projection, and the second one, that is the wedge and dash projection. This is the wedge and that is the dash. So now which one is D, and it is D configuration or L configuration? How to understand? Okay, so you have learned already. So take this structure. First, we have to find out that asymmetric carbon. This is the D-glucose. So find out the asymmetric carbon. How many asymmetric carbons are there? There are 4 asymmetric carbons. So first this one, second, third, and fourth. And we have to consider the bottommost, the asymmetric carbon. Okay, so you take the bottommost asymmetric carbon. Now look here, that OH group in which side? If it is at the right side, it is called D configuration. If it is at the left side, that is called L configuration. So I hope that you have understood that how to understand that which one is deconfiguration and which one is L configuration. Okay, so again I am telling you have to take the asymmetric carbon, then take the bottom side, then write which one is the right side and which one is the left side. You have to think about this. So now take the compound that is the glyceraldehyde. You have seen this one. So here it is represented by the Fischer projection. Okay, by Fischer projection, you can see that OH group at the which side, right or left? First, you have to find out the asymmetric carbon. Here is only one asymmetric carbon, and the OH group I told that is at the right side. So apparently what you will say, that is the D-glyceraldehyde, but it is not the D configuration. Why? We have to take this CHO, this aldehyde group at the top. Okay, for the glyceraldehyde, we have to take this aldehyde at the top. Then what we can do, we can rotate this CHO. Okay, we have to take it at the top. So we can rotate. Okay, then you can get that OH group at the which side, left or right. So now as per the configuration, it is at the left side. So basically it is L configuration. Okay, so in this way, we have to see the different types of projection, that is representation. Then we can determine that which one is D projection, D configuration, and which one is the L configuration. Okay, now you have understood that how to determine the D configuration and the L configuration. Now the optical activity you have learned before. In the first lecture, you have learned what is the optical activity. That is the property of rotating the plane polarized light is called optical activity. So it can rotate either in the left side or in the right side direction. So here the optical and chemical method make it possible to determine the absolute configuration of practically any molecule. In the most modern scheme for specifying absolute configuration, glyceraldehyde is designated R. Okay, see here. Okay, glyceraldehyde is designated R positive glyceraldehyde, and glyceraldehyde is designated as S minus glyceraldehyde. The letter R and S denote the absolute configuration at the asymmetric carbon atoms according to a set of rules that assign priorities of 4 attached atom or groups. And the positive and negative signs indicate the direction of the optical rotations. Okay, so now look at the following picture, then you will be more clear. So optical activity, you know, that is the L isomer, L for levorotatory, that means which rotate the plane polarized light at the left direction. And this is the D isomer, that is the D isomer it is the dextrorotatory. That means it rotates the plane polarized light at the right direction. So levorotatory, what I told, it rotates the plane polarized light at the left direction, and dextrorotatory D isomer, that rotates the plane polarized light at the right direction or clockwise direction. Right side or clockwise, left side or anti-clockwise direction. So here, this is the two isomers. You can see these are the mirror image. This is the mirror and they are the mirror image. One is D-glyceraldehyde. We have kept the aldehyde group at the top. Okay, as per rules, we have kept the aldehyde group at the top. Then our OH group at the right side. So this is the D-glyceraldehyde. And here, this is the OH group at the left side. So it is the L-glyceraldehyde. So they are optically rotate in different way. First, it rotate in clockwise direction, another rotate in the anti-clockwise direction. Okay, so you have understood the optical activity of these isomers. Next is the cis and trans isomers. So to tell about this, we must know the types of the isomers that already you have got, that isomers mainly two types, constitutionals and stereoisomers. So constitutional isomers also can be called as structural isomers, and the stereoisomers is of two types, that is configurational isomers and the conformational isomers. So in conformational isomers, we get the geometric and optical isomers. So optical isomers we have learned in the third lecture of the stereochemistry, that is the enantiomers, two types, enantiomers and the diastereomers. So we have learned these two in the third lecture. And another is the geometric isomers. The configurational, that is the geometric isomers. So geometric isomers is of, I will tell about the cis isomers and the trans isomers. They are the geometric isomers. So cis and trans configuration. So it is under the class of geometric isomer. It exists in alkenes, organic molecules which have double bonds. When two similar or higher priority groups are attached to the carbon on the same side. Okay, so this is called cis isomers. When two similar or higher priority groups are attached to the carbon on the same side, it is termed as cis isomers. When it is attached to the opposite side, it is called as trans isomers. So here you can see from the figure, okay, that is the cis isomers and the trans isomers. So this higher priority group or bulky group, they are, if at the same side, this is called cis. First one is cis and second one is trans. Okay. And now, so for the cis isomers, the greater steric repulsion will be there because of the bulky group. So here this CH3 methyl group and this CH3, this methyl group is at the same side, that is called cis isomers, and CH3 here in the second picture, CH3 in the opposite side, that is called trans isomer. So here the least steric repulsion is here because the CH3 is the bulky group and H is the small group. So less steric repulsion. But the first figure, For the cis isomer, there will be greater steric repulsion because there are two bulky groups. Okay, clear? So you have understood the cis isomer and the trans isomer. Next, I will tell about the racemization. So what is racemization? Racemization in organic chemistry occurs when a compound undergoes a reaction and the transformation produces an equal mixture of both possible enantiomers, sometimes called racemic mixture. So you know that what is enantiomers? Can you remember what is enantiomers? Enantiomers they have the mirror image, but they are non-superimposable. So they are isomers are non-superimposable mirror image. Okay. So when two compounds are classified as enantiomers of one another, it means they are non-superimposable mirror image. For example, consider the two enantiomers of amphetamine. So here you look at this picture, they are the enantiomers. So these two both are the mirror image, but they are non-superimposable. Okay, so if after any reaction we get the equal mixture of possible enantiomers like 50%, 50%, then it is called racemic mixture. So let's get one example. So you have understood that these two compounds are perfect mirror image one another, that they are the enantiomers, but if we try to superimpose, they will not. Okay, so the examples, it turns out the amino acid. So we are taking the amino acid, the building blocks of protein of our body structure, can actually undergo racemization if they are, okay, if they are exposed to basic condition. So here you can see this is exposed to basic condition. There is OH minus. They are exposed to basic conditions. The reaction is constantly shuttling back and forth. So at any given time, there is 50-50 mix of both enantiomers. In other words, they are the racemic mixture. Okay, so in the product, if we get 50-50, both isomers will remain in equal percentage, then this is called racemic mixture. So when each enantiomers is converting to the other, they both go through the same flat planar intermediate. This is an important part of racemization, as we will see in the next section when we study the mechanism. Anyways, so if we summarize today's lecture, what you have learned today. Number one, what you have learned? Number one, you have learned the different configuration, DL configuration, DD and DLL configuration. You have learned the geometric configuration, that is the cis configuration and the trans configuration. And also you have learned racemization. So let's look at the questions. What do you mean by racemic mixture? So you can, I hope that you can answer that what is the racemic mixture. So if you, after any reaction, if we get the same amount of enantiomers, then this is called the racemic mixture. That means the both we will get 50:50. That means 50-50. Next question, what do you mean by DD and LL configuration? So you can explain very well. You have seen, you have observed the video, and so you can visualize that what is the DD configuration and what is LL configuration. So first of all, that means you have to take a Fisher projection of the structure. Then you have to look that the main group, like aldehyde group, will be at the top position. Then the hydroxyl group will be at the right side or left side. On this basis, you have to check that it is DD configuration or LL configuration. Also, you have learned that optical activity, that when it rotates clockwise direction, the plane, if it can rotate the plane polarized light in clockwise direction, that is the dextrorotatory. And if it can rotate at the anti-clockwise direction or left side direction, that is called levorotatory. So you have learned the optical activity also of the isomers. So you have totally what you have learned in the stereochemistry. You have learned the what are the stereoisomers, different types of stereoisomers, the optical isomers like the enantiomers, diastereomers, and the geometrical isomers, the cis and trans isomers. Also, you have learned the optical activity, chirality, and you have learned different representation like Fisher representation, Newman representation, dash wedge representation, etc. And also you have learned different configuration, DD configuration, LL configuration, and racemization. So you go through the entire study material, solve all the question answer, and upload your assignment. Then if you have any doubt, you can communicate with me. And now I have created a quiz for you. This one, basically, if you can take part in this, then it will be, you can understand very well. Still, I am showing. Okay, so I have created, and I will share this code. Okay. Now, if any player in taking the place, then it can be started. Okay, so in this way, you can see your score. So there are different questions. If it is correct, then I am getting the score. Okay, that is 100% accuracy. So another second question, you can see basically when you will play the game, you can see it like the two compounds are shown below are like there are the compounds given. Okay, constitutional isomers or diastereomers or enantiomers. So that is, you can see the structure. Okay, if I am doing that correctly. Okay, so my point is increasing. game you will enjoy a lot. And you can see your score. Okay, game ended and only one player, myself. So you play, then you will enjoy. There is the first, second, third, everything, and you will be very happy. Okay, so for today, I am ending my session. Thank you, everyone.